Chapter 8 and 9. So we are going to start talking about alkanes and alkynes. I will talk about both chapters together as alkanes and alkynes share a lot of similarities in their reactions and preparations. So I'll do all my best to give you the exact section number for each topic so you can go back to your textbook and read through if you need to. So if you think about structures of alkenes and alkynes, they are very similar. The difference between them is that alkynes have 2 pi bonds and alkenes have 1 pi bond. So a lot of the times we'll see similar mechanisms for alkenes and alkynes, but alkynes mechanism can happen twice due to that extra pi bond. So this is why they are very similar to each other in terms of reactivity, and I'm going to talk about both of them together in this chapter. We already talked about elimination in chapter 7 and you learned about alkenes more than alkynes, but here I'm going to start talking about alkynes a little bit before we start talking about their reactions. So the smallest alkyne is acetylene, is a colorless gas, and it is used as precursor for preparation of heavier alkynes. We are going to talk about that type of reactions in section 9.10, where you can basically deprotonate the terminal carbon in acetylene, and therefore it becomes a good nucleophile, so it can react with alkyl halide through SN2 type reactions to form longer chain of alkynes. Alkynes are less common than alkenes in nature. However, a good example can be this molecule. This molecule acts as a toxin and secreted by a South American frog. So the molecule is very toxic, and if someone happened to touch the skin of that frog, this molecule is strong enough to poison and kill that person. Another example of an alkyne that can be synthesized in the lab is this molecule. So this molecule is found in many birth control pills. So these are just a few examples of alkynes in the real world. Now we are going to talk about a little bit about their nomenclature and their reactions. Alkene and alkynes nomenclature is almost similar to what we did for alkanes in chapter 4. So again, you need to find the parent chain, number the parent chain, find the substituent, and put the name of the substituent in the alphabetical order before the name of the parent chain. Now, there are a few things that you need to consider while naming an alkene and alkyne. So first thing is that you want the double bond and triple bond be part of the parent chain. So you need to find the longest chain possible that includes the double bond and the triple bond. Also, the double bond and triple bond should get the lowest number possible. So if you look at this example, we need to number this molecule from left to right, because if we do that from right to left, yes, the substituent would get the lowest number possible, but it doesn't matter. So we want the alkene and alkyne gets the lowest number possible. So this is the correct way of numbering here. Now we have 3 substituents, 2 methyls on carbon 5 and 1 on carbon 6. So we are gonna put all of them together. Therefore, it's gonna be 5,5,6 trimethyl. And we also need to show the location of triple bond in the molecule. So it's gonna be 2 heptine. We call that heptine because the parent chain has 7 carbons. Now, we also have a terminology that we need to be aware of. So we can have terminal alkyne or internal alkyne. So the terminal alkyne has a hydrogen attached at the end. Okay, so the terminal alkyne is one of the useful alkynes because with the base we can deprotonate this carbon and convert the alkyne to the good nucleophile and do a lot of reactions with it. However, the internal alkynes lacks that hydrogen, so we have alkyl groups connected in both sides of the triple bonds. So this slide is just a summary of atomic orbitals that we talked about in chapter 1. So alkene has 1 pi bond and it is sp2 hybridized, and alkyne has 2 pi bonds and it is sp hybridized. So we need to focus on reactivity of an alkene and alkynes and how are they going to react in reactions. So there is a pi bond in both functional groups, meaning that there is an electron density, and even alkyne has more electron density because it has 2 pi bonds. Now if you look at the electrostatic potential map, it's actually pretty interesting. So the red part means that we have high electron density and the blue part means that we have low electron density. So by looking at this map, we clearly see where the pi bond is located, we have the highest electron density. And we know that in reactions, electrons are reacting, therefore the reactive part of an alkene and alkyne will be the pi bonds. Also, if you remember from chapter 3, sp hybridization was more acidic than sp2 and sp3. So the pKa of an alkyne is lower than alkene and also lower than alkane, and the difference is pretty large between alkyne and alkene, meaning that alkyne can act as an acid while treating with a very strong base. So we can deprotonate an alkyne, and that's going to be the start of so many nice reactions that alkyne can undergo. A good example of a strong base that can deprotonate alkyne and form alkanite ion is sodium amide. So this is the structure of sodium amide that can remove the proton and pushes the bonding electron over carbon to form the product. So if you look at the pKa values for both acids in both sides of the reactions, alkyne has the pKa of 25 and ammonia has the pKa of 38. So obviously ammonia is a weaker acid, therefore the equilibrium prefers formation of that. Meaning that sodium amide is strong enough to deprotonate the alkyne and pushes the equilibrium towards the product. Now, if you are using a weaker base, such as hydroxide, so again, let's compare the pKa values. So for alkyne, we know pKa is 25. Now, water has the pKa 15.7. So obviously, water is a stronger acid. Therefore, the equilibrium prefers formation of the starting material. So sodium hydroxide is not strong enough to remove the proton from the terminal alkyne. Now in your textbook there is a table 9.2, that gives you the list of bases that can deprotonate a terminal alkyne. Basically bases of conjugate acids with pKa more than 25, such as sodium amide, can deprotonate an alkyne. This slide is also a review of what we learned in chapter 7. So elimination is a reaction that can form an alkene. Now to form an alkyne, that should happen twice. So a strong base can take the beta proton, forms a double bond and kicks off the leaving group. Now for alkyne, we need alkyl dihalide. So we need a substrate that has 2 leaving groups and 2 beta protons. And we also need to have 2 equivalent of strong base. That 2eq means that we need double the amount of the base to run this reaction. So we can form 2 pi bonds in the product. So this process is happening through E2 mechanism that we learned about in chapter 7. So the E2 mechanism is a one-step process and it is concerted. So we still have one-step process, but it is happening twice. And because it is happening twice, that doesn't mean it is not concerted, okay? So it's happening through E2 mechanism. Now we can start preparation of an alkyne with 2 types of dihalides. We can have geminal dihalide, meaning that both halides, both leaving groups, are on the same carbon, or we can have vicinal dihalides, meaning that both leaving groups or halides are on neighboring carbons. With both of them, we are going to get the same product. So in the top mechanism, a base will take the beta proton forms a double bond and kicks off a leaving group. So we are going to form an alkene that has bromine attached to one of the carbons. Then the base again takes the beta proton, forms the second pi bond, and kicks off a leaving group. So we are going to form an alkyne through E2 mechanism. So since it is a E2 mechanism, again as a reminder, remember that hydrogen and leaving group should be in anti-preplanar geometry. So if that comes in exam, remember this point. So oftentimes we use excess reagent in preparation of alkyne, and we show that with X and S on an arrow. Now this reaction that you are seeing here, it's something that we just discussed. So sodium amide is a strong base. Now using amide, we can do elimination twice to form an alkyne. Now because we are using sodium amide, and sodium amide is a strong base to deprotonate the alkyne, through acid and base reaction, we are going to form the alkanite ion. So if you want to have your alkyne and you don't want to convert it to alkanite ion, we need to add a separate step to convert the alkanite to alkyne. Now to get our alkyne back, we are going to add a proton source in the second step of the reaction. So here water acts as a proton source. Therefore, the alkanite will react with water through acid and base reaction, and basically we are reforming the alkyne, which is the desired product. Now if you compare the pKa values, obviously an alkyne is a weaker acid comparing to water. Therefore, the equilibrium prefers formation of the product. So once again, let's review what happened. So sodium amide, which acts as a strong base, react with the substrate, with dihalide substrate, and forms the alkyne. Now because sodium amide is very strong base, it can deprotonate the alkyne to alkanite ion. And again, we are going to add a proton source to the reaction, so we are reprotonating the alkanite to get the desired alkyne. Now let's look at this example here, the reaction here, and predict the product. So let's draw its mechanism together. Now on the arrow, as I said, most of the time we are going to see XS, which means excess reagent. So we have excess sodium amide, and so okay, so we have beta protons here. So what's happening is that sodium amide or amide itself, it will act as a base, take the proton, the beta proton forms a double bond and kicks off the leaving group. So we are going to form this alkene, and again because we have excess of amide, it will react one more time with the beta proton, forms a double bond and kicks off the leaving group. So we know that alkyne is linear, so we need to draw a linear alkyne. And every time amide takes the proton, it converts to ammonia. So just don't forget that it converts to ammonia. Okay. Now because sodium amide is a strong base, and again we have it in excess, so it will react let me draw the proton so it's more clear. So through acid and base reaction, take the terminal alkyne proton and we are going to form this product. Okay, so we have alkanite anion right now. Now to regenerate our alkyne to get the product that we want, in the second step water is added. So after adding water, through acid and base reaction, we are gonna reform the alkyne. Okay, so the answer for this question would be this structure. Till now we know how to make alkenes and alkynes, and now we want to see what type of reactions they can do. So we are going to talk about addition reactions. So the name can tell us what's happening. We are adding something across the double bond. So here we have a double bond, a pi bond. So we are gonna break the pi bond, and instead we are adding two groups across the double bond to the corresponding carbons. So in many cases, addition reaction is just the reverse of elimination reaction. So imagine if you have a double bond, a pi bond, and you want to add HX across the double bond, such as HCl, HBr. Now, when you add hydrogen and halogen across the double bond, we are going to form this structure. So this structure is a alkyl halide. Now, if you have a strong base, you add it to the alkyl halide. This is the beta proton. You can do elimination and form the alkene. So they are basically opposite of one another. Now, addition reaction is an exothermic process. So we don't normally have to add energy to help the reaction go. So it can happen at room temperature. However, the reverse process, which is an elimination reaction, is endothermic. So we need to add energy to help the reaction go. So sometimes instead of talking exo and endo, you may see low temperature or high temperature for elimination on the arrow to show that basically addition is exothermic and elimination is an endothermic process. The first addition reaction that we are going to talk about is hydrohalogenation. So basically the name can tell us that we are going to add hydrogen and halogen across the double bond. And the reagents that we can use, it can be HCl or HBr or HI. So for example, if we take HBr and the alkene bond, we are going to break the pi bond, and instead of the pi bond, we are going to add hydrogen and halogen across the carbon-carbon bond. Now, if the alkane is not symmetrical, meaning that we have different groups attached in both sides of the alkene, we need to decide which carbon gets the hydrogen and which one gets the halogen. So here we have a rule that says hydrogen adds to the less substituted carbon, and halogen adds to the more substituted carbon. So we call this rule Markovnikov rule. So Markovnikov is the name of scientist that discovered such a rule, which says hydrogen adds to the less substituted carbon and halogen adds to the more substituted carbon while doing hydrohalogenation across the double bond. As I mentioned, hydrohalogenation is regioselective and we are going to form Markovnikov product, meaning that the hydrogen will be added to the less substituted carbon and halogen will be added to the more substituted carbon. So let's look at this example. Okay, so this is our alkene which react with HCl. So if you look at this carbon has only one substituent. However, this carbon has two substituents. Therefore, hydrogen will be added to the less substituted carbon and halogen will be added to the more substituted carbon. Now let's look at the mechanism for hydrohalogenation. So let's look at this example once again. So during hydrohalogenation, we are going to form a racemic mixture. So what does that tell us? If you remember from SN1 mechanism, we also made racemic mixture during SN1 mechanism, and that was because we formed a carbocation. So that tells us here that this mechanism involves formation of a carbocation. Now let's look at the starting material that we have. So we have an alkane that react with HBr. So HBr has the proton source. Now where the electron density is in this two starting materials? So obviously it is on the alkene because it has a pi electron. So the pi bond, which has pi electrons, would act as a base, attacks the proton, and kicks off the bromine. So we are gonna form, so bromine leaves, now to drop the product, which carbon would get the proton? Carbon 1 or carbon 2? So if carbon 2 takes the proton, we are gonna have this structure, this carbocation will form. Now if carbon 1 takes the proton, we are gonna form this carbocation. Now which one is more stable, the bottom or the top? Obviously the top carbocation is more stable because it is the secondary carbocation. So hydrogen will be added to the less substituted carbon so we can form the more stable carbocation. The bottom product is not forming. Now in the next step, so we kicked off the bromine. So bromine acts as a nucleophile and attack the carbocation from the top and from the bottom to form the racemic mixture. So just remember, we are forming a racemic mixture if we are forming a chirality center. If we are not forming a chirality center, we are going to have one product. An example for that is right here. So after addition of hydrogen and halogen across the double bond, we form this product. Now in the product, we don't have any chirality center. So this is not a chirality center, this is not a chirality center, therefore this molecule, we are only making one molecule. However, when you make a chirality center in the product, you are going to form a racemic mixture. Now, another important note here is that during hydrohalogenation, we are forming a carbocation. So since we are forming a carbocation, we need to consider the possibility of rearrangement for the carbocation. So if the carbocation can do rearrangement to form the more stable carbocation, it will definitely do it. And also, once again, so the hydrogen is added to the less substituted carbon to form the more stable carbocation, and then bromine is added to the more substituted carbon to form the product, which is following the Markovnikov rule. Now, there is a way that we can add halogen to the least substituted position, and we call that anti-Markovnikov process. So scientists found that if they use alkyl peroxide is ROOR, that R group is an alkyl. If they use that with HBr, addition of HBr is going to be anti-Markovnikov, meaning that bromine will be added to the less substituted position and hydrogen will be added to the more substituted position. So you don't need to know the mechanism here. It's a radical mechanism and you are going to learn about that in organic chemistry too. However, we need to see what's happening in the reaction. So if you look at this example, we still have an alkane and we are still using HX such as HBr. Now if you add alkyl peroxide, a trace of alkyl peroxide is enough. We see that bromine will be added to the less substituted position and hydrogen will be added to the more substituted carbon. So addition here is anti-Markovnikov. Okay, so hydrogen goes to the more substituted and bromine goes to the less substituted position. Alright, so the important point here is that when you have a HBr addition is Markovnikov, meaning that the hydrogen will be added to the less substituted carbon and bromine will be added to the more substituted carbon. As soon as you add alkyl peroxide, the addition will be anti-Markovnikov, meaning that hydrogen will be added to the more substituted position and bromine will be added to the less substituted position. Now let's look at a few examples here. So in the first one, we are adding HBr to the carbon-carbon double bond in this molecule. So to draw the answer, we know that hydrogen should be added to the less substituted position, which is this one, to form this carbocation. Now, can this carbocation do rearrangement to form a more stable carbocation? No, this is the most stable one. Then in the next step, bromine will act as a nucleophile and attack the carbocation to form this product. Now, do I get racemic mixture? Do I need to show stereochemistry here? No, because this carbon is not a chiral carbon. So this is the only product that we can get. Now in the second example, we are using HBr and alkyl peroxide. So the moment that we are adding alkyl peroxide, addition will be anti-Markovnikov. And we know that the mechanism for this reaction is radical, so we are not even forming a carbocation. But we know that hydrogen will be added to the more substituted position and bromine will be added to the less substituted carbon. So the product for this reaction, So the more substituted carbon is this one. Hydrogen will be added here. Addition is anti-Markovnikov. And the less substituted carbon is this one. Bromine will be added there. So this is gonna be the final product. Now for the third one, we are only using HBr. So again, addition is Markovnikov, meaning that hydrogen will be added to the less substituted position and bromine will be added to the more substituted position. So we are forming a carbocation. So I'm gonna draw the carbocation that we are forming. So hydrogen will be added to the less substituted position, which is this one, and forms this carbocation. Now, can this carbocation do rearrangement to form a more stable carbocation? No. So therefore, in the next step, bromine will act as a nucleophile, attacks the carbocation to form this product. Now, do I need to show stereochemistry here? No, because this carbon is not a chiral carbon. This part of the molecule is the exact similar as this part, so it's not a chiral carbon. And that would be the only product for this reaction. Now, the exact same process can happen when we have alkyne. The only difference here is we have 2 pi bonds with alkyne, meaning that that reaction can happen even twice if we use excess reagent. So if you look at the top example, so this is what we just discussed. We have an alkene that react with HX, addition is Markovnikov, so hydrogen will be added to the less substituted carbon and halogen will be added to the more substituted carbon. Now in the exact same process, if you are using one equivalent of HX, so if you are using only one equivalent of the reagent, hydrogen will be added to the less substituted position and halogen will be added to the more substituted position. So addition is again Markovnikov, exact similar as alkene. So sometimes that might be hard to follow the number of carbons. So that would be a good idea if you number all the carbons. So the pattern of numbering does not matter. We just need to number the carbons to keep track of them. Now if I number that, 4, 5, and 6. So we are adding across carbon 5 and 6. Now 5 and 6 is an alkyne that converted to an alkene. So we know that alkene is not linear anymore. We are drawing it in a zigzag format. Now, if we add excess reagent, so I'm gonna draw the exact same molecule. If we add excess reagent, we show excess by X and S. So we are gonna add both halogens to the same carbon and hydrogens to the same carbon. So what's happening here? Let's number all the carbons first. 5 and 6. 5 and 6. So we are adding H and X across the pi bonds between carbon 5 and 6 twice. So the intermediate here is this halogen, alkene basically. So we are forming this alkene with one equivalent of reagent. Now if we add another equivalent, hydrogen will be added to the less substituted position and another halogen will be added to the more substituted position, which caused that we ended up with both halogens on the same carbon. So, oh, and don't forget that X means halogen and hydrogen is hydrogen. So we are going to form geminal dihalide here. Similar to alkene, we can see anti-Markovnikov product with alkyl peroxide with an alkyne as well. So if you look at this example, now I'm going to use HBr with alkyl peroxide, and these are going to be the products. Okay, so this is the trans isomer and this one is cis isomer. So addition is anti-Markovnikov, meaning that hydrogen will be added to the more substituted position and halogen will be added to the less substituted position. So it is shown here, and we are going to form a mixture of cis and trans isomer. So in this case, in this reaction, we are not going to see excess HBr. And we are only going to use one pi bond to form a mixture of cis and trans product. Trans is more stable, so it's going to be our major product here. So this is our major product. Now let's look at this example. We have geminal dihalide that react with excess sodium amide, and in the second step we are going to add water, and then in the third step we are going to add HBr and alkyl peroxide. So if you remember from the previous video, while we were making alkyne, so when we are using excess sodium amide, we are going to do elimination twice on a dihalide molecule to form the alkyne. So step 1 and 2 gives us this alkyne. Now adding HBr and alkyl peroxide in the third step, we are going to form both cis and trans isomer. So addition is anti-Markovnikov. Bromine will be added to the less substituted carbon and hydrogen will be added to the more substituted carbon. So we are going to form both isomers.